Good morning, everyone, and welcome to day 5 of the Qiskit Global Summer School on Quantum Simulation. I am thrilled to be with you. You folks have devoted 2 weeks in favor of launching and further propelling your quantum journey and quantum career. So I have no doubt that we're going to have some fun today. I want you to know that it really is my ultimate pleasure and privilege to be here with you today and be your lecturer on this new journey. So, our aim today is to help you gain the skills and know-how to explore the real world of quantum computing and its applications, which is why we're going to talk about quantum noise. In this lecture, we'll answer the following question more precisely. What do I need to know before I run a quantum simulation on a real, noisy quantum processor, the kind that you can log into the cloud right now, and you will shortly in your labs? Now, in no way will our answer be fully exhaustive. Rather, we're going to take a narrow but deep path into the world of real quantum simulations that will allow you to hit the ground running quickly and to go far. Our focus will be on the big ideas, and I will help expose to you through the lens of concrete and manageable small examples some of those big ideas that I hope will stay for you for a long time and will be helpful and useful on your journey. So don't be shy. We're all here for you. Ask questions as we go along and I'll help answer them in the Q&A period. Now, with that, I hope you're excited as I am. Put the thumbs up in the chat if you are, or the right emoji, and let's get going. Staying with tradition, let us start with a hello world example in a real quantum processor. On this slide, we've depicted a specific quantum system, one kept inside the superconducting fridge with some experimentalists, say, working on it. Let's say that inside of this fridge, there is a qubit. I'll use this cartoon to depict how much we're going to abstract away about what the real qubit actually is, how it's made, so and so on. I cover that in my QGSS or Qiskit Global Summer School 2020 Summer School lectures. So if you want more depth, you can find them on the Qiskit site or YouTube. And amazingly, for the rest of this lecture, we don't really need to worry about any more of those details. For now, it really just suffices to say that a qubit has two computational basis states, conventionally labeled as 0 and 1, placed inside the little ket symbol to denote that these are not classical computational states, they are quantum and therefore have more information content capability than classical states in some sense. To manipulate this quantum information in the qubit, we can apply operations to the qubit. A simple operation is the NOT operation, denoted by X and pictorially represented by this X in a box. To refresh our memory from earlier in the week, what this X gate or NOT gate on a single qubit does is it flips when applied to the 0 ket, it flips it to the 1 ket. And when applied to the 1 ket, it flips it to the 0 ket. Simple and symmetric. So we're going to stick with it for a little bit in the beginning. Now, in addition to quantum operations, we need some quantum to classical operations as well to extract results from the quantum experiments that we can receive classically. We can also measure the qubit using some meter apparatus, such as depicted by this little box here with the meter symbol inside. And in principle, this meter can measure all kinds of things and properties about a qubit. Conventionally, we're going to stick with a property known as the Z component or Z value, and we'll get more into that. But recall from lectures 1 to 4 that the Z operation, or the phase flip operation, has the following property. When applied to the 0 ket, it spins it right back out with a plus sign, and when applied to the 1 ket, it spins it back out with a minus sign. In other words, the 0 and 1 ket are eigenvectors of this operation. They don't change. The only thing that happens to them is that they get multiplied by a value, the eigenvalue, and in this case 0, in this case plus 1 or minus 1. For our hello world example, suppose we want to use those ingredients to create an interesting, to play with simple algorithm that, let's say for the purpose of this lecture, we can do the following. Let's say we want to classify or report whether a classical positive integer that we somehow supply to this algorithm is even or odd. So the algorithm should return, let's say, +1 if the classical parameter that we give it, such as the integer 3, 5, 7, or so on, if that classical parameter is even, such as 2, 4, etc., or -1 if that parameter is odd. So suppose we want to do this with simple bit flip sequences. This is one way to implement it. Suppose that we flip our spin exactly the number of times that this integer has been given to us. So for instance, here we can flip the spin 1, 2, 3, 9 times in total because we've given an integer 9 and we'd like to recover an answer. So let's examine what this will look like. We'll call it the qubit flipper quantum circuit. So let's look at the actual circuits associated with this algorithm. And one way to do it is the following. First, let's initialize the qubit in the ground state, denoted by ket0, as it is conventionally always the starting state of our quantum algorithms. Now, in the very first instance, or let's say that we had the integer 0 given, all we have to do is then measure the qubit. If, on the other hand, we had the integer 1 given to us, we would just apply the bit flip operation one time. Let's say 0 will then get flipped by the x gate and will then be measured. And so on. Now we could create a whole sequence of these to understand what this algorithm does as a function of each of its input parameters. So we're going to look at that and see what that looks like. So we can extend the depth, or in other words, the number of times that we have applied this gate x to larger and larger circuits, and so on. So repeating this many times as we want, what does this sequence do? Well, to answer that, let's use our quote-unquote quantum debugger to step through the algorithm. At the start of the experiment, here denoted by the dotted vertical red line, all the different circuits are initialized in the 0 state, so we can understand that quite well. After the first step, the first circuit up here is going to be measured, and the rest will be flipped. Now, all the ones that are flipped will, of course, take 0 to 1 for the state of the qubit after that first step. How about the measurement? Well, in this first step, our measurement in the measurement apparatus will yield a classical result of +1, since the expectation value of the z observable, which is our measurement basis, is +1 for the ground state 0. Remember the refresher we looked at. We'll return to cover measurements in more depth and why you do it this way and so on, but for now take this as the answer. In other words, the first circuit will deterministically produce a +1 classical result. Now how about the second circuit, after 2 steps when it's measured? Because the state here is no longer 0 but now 1, also an eigenstate of the z operator, the measured outcome here will deterministically be -1. And stepping through the circuit like this, going over to step 3 and step 4 and so on, we'll see that the result, as the depth is increased by 1, alternates from +1 to -1. In other words, the expectation value of the observable we want to measure as a function of the depth of this circuit is an alternating series of +1s and -1s, which we can write as this expectation value of z is equal to -1 to the power of the depth d, where d is the integer denoting how many x gates are in the particular circuit. Okay, so let's visualize this on a plot. On the y-axis of this plot, we can plot the measured expectation value, z, as a function of how many times we have flipped the qubit, in other words, the circuit depth. shown here on the x-axis. Now we expect that it's precisely this function, -1 to the power of d. So here's the analytical plot of the outcomes of the measurements that would look at, this is what the ideal results of the experiment would look like in the absence of all errors on the quantum computer. Simply a sequence of alternating +1s and -1s, just like we wanted for our bit flipper algorithm. The y value is +1 for even x and -1 for odd x. Okay, great. We have made an awesome quantum algorithm, right? Time, however, to try it out on the real device. Let's see what happens. Okay, so I'm going to run and execute it. Okay, I'm running, I'm back. Now I'm going to show you the results. I did this earlier, of course, and let's see what we get once we ran it on a real device. Okay, so this is not at all what we expected to see. Whoa, okay, you might say, whoa, you are not very true to us here. You told us we'd see one thing, now we see another thing. You know, what happened? Well, this is the real data of running that experiment. It looks like what we wanted at very low depth, near 0 here. It looks like indeed for 0, 1, 2, 3, more or less you almost got the value 1, not quite. But at high depth, as you go further and further along, essentially you're just seeing noise, and in the middle you're seeing something completely different. So what happened to our ideal, tranquil, beautiful algorithm and all the hard work we put into calculating -1 to the power of t? Well, you might be reminded of the funny cartoon. I hope you find it as funny as I do, that reminds us that, well, rather than storing information in every way possible simultaneously, in this case, your quantum computer seems to be broken in almost every way possible simultaneously. So, what's going on? I'm reminded of this quote by the famous physicist Asher Perez. Quantum phenomena do not occur in a Hilbert space. They occur in the laboratory. Everything we calculated was in Hilbert space. Everything we actually ran was in the laboratory. In other words, real experiments don't occur in Hilbert space. They are inseparable from the imperfections and features of the laboratory and the underlying quantum devices, which are unavoidably subject to noise. Noise causes errors. Noise is unavoidable. You can reduce it, you can try to decouple from it, but you can never fully, truly get away from it. It's here to stay. So we better understand noise and how to deal with it. That's what this whole lecture is about. It's to prepare you and introduce you to the world of real quantum computers, the kinds of things you see out there in the real laboratories, or you can log into the cloud. So let's understand noise and understand its effects, more importantly, on the simulations and algorithms we want to do. So looking back at the data, the raw, real data from the experiment we saw, let's start at the very beginning over here on the left. You can see that unlike our theoretical prediction, even at depth 0, the very first point already disagrees with our prediction. It does not start at +1 as we expected. So what does this have to do with? Well, there is SPAM. SPAM stands for state preparation and measurement errors, or noise. Maybe we didn't prepare the state as ideally as we wanted to. Maybe the measurement was a little faulty. All of these kinds of errors can get lumped into, and we'll talk about how that affects the measurement. Now, next, you notice this guide to the eye that I plotted over here in orange, this dashed exponential decaying curve. It shows you that the data seems to at first decay exponentially. This has to do with incoherent noise. It's a signature of typically incoherent noise, which is in this case resulting in an energy loss, which also will correspond to loss of information. Now, moving along to the right, things seem to change. In fact, the data the curve pinches off and then revives. The data seems to oscillate. Well, this is a typical signature of something known as coherent noise. Maybe our X gate wasn't really an X gate. It was almost an X gate, but not quite. Perhaps there's a calibration error. We'll explore and find out what that is and what that means. And then as you move along to the right, you notice at the very end, essentially all relationship to the initial state is lost, all information relevance is lost. You just more or less are getting pure noise, and yet you don't get an exact value. You're still getting fluctuations around that value, and that has to do with the fundamental projection noise in quantum physics, which you cannot get away from, but you can reduce to arbitrarily small values, as well as still unavoidable spam, which will show up more or less all over the place. So what lies ahead for us today on our journey and on our road? We'll start off with coherent noise and examine that at the single qubit level, returning to this concrete example and keeping that in view. And from there, we'll reveal or look at how measurements work at the level of a theory in a nutshell, to set ourselves up for understanding projection noise, a very important concept. Then we'll look at spam noise, in particular focusing on noisy meters. We won't get into the preparation as much, that will be for the bonus content. Finally, we'll reach incoherent noise, which really opens up a whole new world of quantum physics, and it's quite exciting. You can talk about quantum trajectories, understanding measurements, and so on. Here we'll just introduce some of the most important notions you need to have when you run your next experiment. Finally, we'll touch on what do you do with noise? How do you mitigate it, correct it, undo it, just at a very high level. You can understand noise, you can learn the noise, and if you can do those things, or you can detect it, you can actually also undo it and recover, or at least mitigate it to some level. And finally, for those of you who want to go a little bit deeper, we also have some bonus content on coherent ZZ, two-qubit, multi-qubit noise, as well as more on state preparation. That will be at the end. Now, it's important to remember that here the destination is the journey. We'll start simple and build slow, but each of those steps is going to try to elucidate a larger idea, even though it's a simple example. Let's dive into our chapter 1, coherent noise, and let's look at the effect of coherent noise in this circuit and understand where those oscillations might have come from, why they might occur. The trick to all of this is to really dive into the composition of the X gate and how these gates occur in this case. So let's focus on our NOT gate, and if you go back to the earlier lectures of this summer school, you talked about time evolution and how the actual final change of a state, of a quantum state from, say, 0 to 1 occurs. It's not instantaneous, it's not abrupt. There is a continuous, coherent transition that takes the state continuously from 0 to 1. That's exactly the way that all quantum operations under the hood actually occur, through a continuous way. We call that time evolution. To describe the overall effect of the transition without the details of the path from 0 to 1, we write these boxes on the left and we abstract those details away. But the way they're actually realized, of course, is by an underlying physical process that's governing this transition going from 0 to 1. So to describe that, we use a notion, an idea of the Hamiltonian. The Hamiltonian is going to be an operator denoted by H with a hat here to indicate that it's a quantum operation that is going to tell us at each instant in time how the state change will happen. One way to generate this bit flip is to set the Hamiltonian governing the time evolution as h bar, Planck's constant, times omega, some rate of change with respect to time, in angular units typically, divided by 2, as we'll see for normalization reasons why that is, times the x operator itself. Now, I've dropped the hat on the x, as we'll often drop the hats on some common operations, or we'll tend to leave them off further we go along unless there's some confusion on what's classical and quantum. So keep in mind that this capital X and capital letters in general will denote quantum operations. Now, if we go back to your earlier lectures, or if you look at what x does, if you put in a state, let's say 0, x will flip the state 0 into the state 1. So in essence, we can write down x as a matrix in this way, as you looked at earlier in your lectures. If we come in with a state of ket 1, x will take the state ket 1 and it will swap it into the ket 0. So that's why the matrix representing the state transitions in the z basis of x is off diagonal. The diagonals are 0 and 0, and the off diagonals are 1 and 1. This, of course, simply indicates our earlier notion that x on 0 is 1 and x applied on 1 is equal to 0. To understand the total time evolution, or what happens as you evolve the quantum state under the action of this operation, this Hamiltonian, for some total time t, we can write down and use the notion of a unitary. So the total transition from time 0 to time t, so let's write it as time 0 to time t, and time 0 will set always to 0 in this case, is given by the integrated evolution of the Hamiltonian, which is just going to be the exponential of minus I, where I is the imaginary number, times t, that's the total time, times the Hamiltonian normalized by h bar, as this has to be dimensionless. By defining the following parameter, theta, as omega times t, since if we expand h hat over h, the Hamiltonian will have an h bar omega over 2 h bar times x. So we can define an angle that's got no units. It's not time, it's not hertz, etc. It's going to be an angular angle. We can define this angle theta. We can then rewrite this unitary now with the letter r sub x of theta, suggestively, to denote that it will be a rotation, hence the r, around the x-axis, as we'll see what that means in a second, of an angle theta. Notice that while the rotation is of an angle theta, there is still this factor of 2 here in the denominator of the rotation, and that 2 essentially normalizes the spectrum of the x operator, since x is plus 1 and minus 1, so the whole span of plus 1 to minus 1 is 2. And if we now use some trigonometry and algebra, we can expand this out as a Taylor function if you want, this exponential. And from there we can write out and group terms, or if you want you can take this identity as either an exercise or as a given. We can expand this cosine, this exponential, into 2 pieces, one that's proportional to the identity and one that's proportional to x. Essentially the exponential will mix terms in its argument. There's only one term in its argument, it's x, so you won't see anything other than x. X squared is of course the identity, so if we applied x twice, you'll get the identity. You can verify that by looking at the matrix and multiplying that out. So working this out, and I challenge you to do this on the side or to go back and review it, we'll find out that the rotation that actually generates this gate is written out as this. The gate x can actually be derived from a rotation around the x-axis of a particular angle, and that angle is going to be pi. If you put in pi in here into this expression on the right, you'll see that the first term is going to disappear and will go to 0. The second term will give you just an x. However, the sine of theta over 2 will remain will give you some global phase, and we're going to ignore that as an operation overall, as your earlier lectures covered why global phases in this case are not relevant. Let's visualize this on the Bloch sphere. In the Bloch sphere picture, the state of the qubit is represented to remind us as an arrow of unit length. The tip of the Bloch sphere up here at the very top is the zero state or the ground state. On the other hand, at the very bottom of the sphere, the point down here at the south pole represents the one state. The states in the middle are superpositions of those two states. For a qubit that, say, starts in the ground state up here at 0, we will now apply a rotation r sub x of an angle theta. Now, the reason that we will denote this r sub x as a rotation around x is because if you want, the generator of that rotation is x. And you can think of visually what is going to happen to the arrow of the qubit after the application of that gate as a rotation in this sphere around the x-axis. And so you can take your right hand and use the right hand rule, putting your thumb up along the x and curling with your other fingers to see that the application of this gate will take the 0 vector and move it towards 1. And that's going to represent this operation exactly of cosine of theta over 2 on the identity gate plus sine of theta over 2, and excuse me, it's minus I sine theta, not plus, on the x hat. So visually, what does that look like? Well, essentially, as a function of the angle theta, the state will rotate through this trajectory, and theta will determine how far it will rotate. So for the angle theta equals pi over 2, the state will rotate exactly all the way from the north hemisphere down to the south hemisphere, following this trajectory illustrated here in this picture. Now, that's the dynamics going on underneath that X gate that we looked at earlier. So far, we had abstracted all that away and simply repeated it. Right. Underlying that, of course, is this actual continuous time rotation. Now, how do we know we got the right angle theta? Or how can we trust that it's correctly calibrated, or it hasn't drifted since the calibration of the quantum processor? And this is where we'll have to touch base on the errors. Now, before we do that, let's also just remind ourselves what happens if you continue the angle theta. If you increase the angle theta, you can simply continue all the way and come back to 0. So you can do a full identity rotation too. So this unitary evolution for different angles theta or for different times allows you to implement different gates, such as the square root of x, or even the identity gate through this whole evolution. So with that in mind, the actual evolution of our algorithm looks like the following. We've initially prepare and start the state in ket 0, which is this red arrow at the very tip. We can then take that arrow, and after one application of the X gate, essentially in time, the sequence looks like it has done the following. The state starts at 0 and then rotates all the way down to the south pole, which is where it's at 1. And in that case, we're at the end of this first wire. If you apply 2 gates, once you're at that first wire, you've now continued to rotate yourself all the way again back to the North Pole. This is all great, but who's to say that we've precisely timed our angle so that it's precisely a pi rotation? What happens if we're just a little bit off? Let's take a look at that. Suppose that instead of the ideal noise-free gate, which we denoted by x here on the left, and visually we've shown its action on the qubit below, suppose that instead our gate suffers from a very common coherent error of over-rotation, meaning that instead of our ideal gate, we rather have this noisy version of the gate. And visually, I'll depict its action first as this over-rotation. If you can see down here, it just goes a little too far. Maybe we miscalibrated, maybe things drift. the noisy gate will denote by x tilde. The tilde will mean that it's the noisy version. And in our experiment, we only get to apply this noisy gate because that's what the processor has at the moment. Algebraically, our model of that, of course, can be that x tilde we just define as the same rotation around x. It's just now that the angle isn't pi, it's pi plus epsilon, where we can think of epsilon as some small angle, though it doesn't have to be. Clearly, when this rotation is done, starting in the 0 state, after the application of this gate, we will no longer be in the correct 1 state. Let's expand and see what the small angle actually does by substituting the expression for the noisy gate, for the rotation into this expression. Essentially, the only thing we have to do is take the angle pi plus epsilon, call that theta, and then use the, if you want, the expansion into sines and cosines. But even without breaking things up into sines and cosines, we can immediately just substitute these two expressions to obtain the following. Now, inside the argument of the exponential, we simply have numbers getting added, so we can break that fraction up into two fractions, which very much look like two angles being added together. Because these two arguments, the first here and the second, are proportional to the same operator x, those arguments commute. So clearly x commutes with x as a good operator, it commutes with itself, and therefore we can just treat this expression as if it was classical numbers, essentially, for the second, and so we can break this exponential up into the product of two exponentials. Of course, if the first argument was x and the second was y, here you couldn't do that because of the non-commutativity of x and y. However, because it's the same x in both cases, it's the same operator, they commute, and we can break up our exponential in these two ways. Looking back up to the top here, we recognize that each of these is just a rotation. In other words, a rotation of an angle pi plus epsilon is just equal to a rotation of an angle pi followed by a rotation of an angle epsilon. And you can visually see that, of course, as seeing that this first rotation here had an angle pi, this second rotation here had an angle of epsilon. More generally, what we've just shown is that around the x-axis, or really any axis, the rotation of two angles, the sum of two angles, is the product of the rotations. That's a very handy and useful thing to keep in mind. Visually, what you have just seen, or what we have just accomplished, is a decomposition, an equivalence relationship that breaks up the noisy gate x tilde into two gates, the ideal gate x, in this case preceded by the noise, which in this case is coherent. So it's some rotation around an angle x epsilon, and we've just denoted that here as x sub epsilon, which just stands for our r sub x of epsilon. These kind of noisy gate decompositions are very useful tools in your toolbox, so keep them handy. A common point of confusion and a common pitfall here is that students often get confused about the ordering. Notice that while in the pictogram x is on the left and y is on the right, when it comes down to the algebra, x is on the right, y is on the left. In other words, you read circuits left to right, but the algebra operations act right to left, the reverse order. So just make sure you keep those straight. Let's apply this new knowledge in our circuit, where, if you recall, we had the ideal gate here on the left. That's our circuit for depth D. The noisy version of this circuit looks almost the same, except that we have now also added this x epsilon error. This is our over-rotation into the circuit. So we can write out explicitly what this looks like. Notice that I have put this bounded box dashed in purple here around the error term and the gate to indicate that you cannot actually separate these two gates. It's not like I get to apply x epsilon without x. If the gate is actually noisy, they're inseparable and I have to apply both at the same time. On the left, our x gate is just the rotation of angle pi. On the right, our noisy gate, x tilde, which we should be explicit and add in here as x tilde, is simply the product of those two rotations, or a rotation of the sum of the two angles pi and epsilon. On the left, the unitary that describes the total circuit here is going to be the x gate raised to the power of d, while on the right hand side, that the total noisy unitary that we will get to apply, which will symbolize the entire right hand side circuit here, is going to be the noisy gate x tilde to the power of d. Writing this out explicitly in terms of the rotations r sub x, just plugging this in on the left and on the right, we have the following two expressions. Again, using this substitution here, which we can use the following trick to simplify. Recall that the rotation around some axis, let's call it x, of angles a plus b, oops, and my pen looks horrible here, I'm sorry about that, is simply the rotation around that axis of angle A times the rotation on that axis of angle B. And so using that d times here, you can find that, and since all of these rotations commute, you can group terms and say that simply the error is going to accumulate in this way, where the total rotation angle of the error is going to be d times epsilon, where d is the depth of the circuit, multiplied by the rotation of the angle d times pi on the right hand side, which is exactly the ideal noise-free unitary. So in other words, the noisy total unitary can be written as the noise-free ideal unitary U total, followed by some over-rotation that has an angle that grows linearly in the depth, d. Let's see what this looks like in terms of the state and how the state is going to evolve. So assume that we start in the ground state for both cases, on the left and on the right in the ideal and in the noisy case. Now, if we expand our total rotation here, we can say that the final state, let's call it psi sub f, or final, is going to be equal to the total unitary times whatever the initial state is, so let's say 0 in this case. And this is just equal to Rx of d pi acted on 0, which is just equal to, using our earlier identity for the resolution of this rotation into cosine of an angle, which is cosine of d pi divided by 2 acted on 0, minus I, notice that there's this phase here, sine of d pi divided by 2 acted on the x, there's the x operator here, acted on the 0 state. Of course, we know exactly what x acted on 0 is. That's nothing other than the 1 state. That's our bit flip. So rewriting this a little bit further, we can see that on the left here, cosine of d pi over 2 is going to give us either 0 or 1. So cosine of 0 is 1, cosine of pi is 0. So we will have this be either 1 or 0 for even and odd respectively. Meanwhile, the sine term is just the complementary of it. It's 1 for d odd and 0 for d even. Perhaps we should write these out more explicitly. So this is going to be 1 for d even, 0 for d odd, And similarly, the sine term will be 1 for d odd and 0 for d even. So combining these into the final result, the final state at the end of this, right before the measurement, is going to be either 0 or 1 for d even or for d odd. Modulo a global phase. We're going to ignore the global phase, which will be here. That's the ideal case. The noisy case is very similar. The only difference is the angle is going to be a bit different. So the final state, psi final, call it tilde for noisy, is going to be equal to Rx of d epsilon times the ideal state, which we now know is, let's say, psi final, which is just going to be either Rx acted on 0 for d even, or this Rx of d epsilon acted on 1 for d odd. And this is supposed to be Rx of d epsilon, excuse me, I forgot to write that in. Okay, so I challenge you here as an exercise to explicitly write these out and see exactly what they are. And instead, we're just going to focus on calculating one important parameter for both of these, because we'll want to plot what it is, and that's the expectation value of the z observable. And in this case, maybe we'll keep in mind that this is the noisy z observable, which is going to be psi final tilde z hat psi final tilde, which you can see is going to be equal to something very related to what we have on the left hand side here, which perhaps we should do also here. So let's do both, just to be more explicit. The first one will be the noisy one, the second one will be the ideal case. For this latter case, let's use the expression here in terms of cosine and sine, since that will handle this for us easily. I'll let you work out the exact detail of it, but you should find that this is nothing other than just cosine of d pi, which simply will take that plus minus value, and that's equal to minus 1 to the power of d, which we saw earlier. In the noisy case, however, we have almost the same expression, except that it will be the cosine of d pi plus d epsilon. Okay. And in the interest of time, I'll let you pause the video if you're watching the video and work this out. And if you're in the live lecture, this will be one of the exercises. So, what do these look like? All right, so on the left here, we can now take a look at the ideal expectation value of z, which we calculated and saw before. Now we explicitly, if you want, to calculate it. On the right-hand side is the more interesting noisy case. We now have the noisy expectation value, which has this extra angle d epsilon. And notice what it does. All it's doing is adding a little bit of a phase rotation that we previously couldn't see. But you can notice that now there's this kind of sinusoidal envelope of the oscillation of the z expectation value as a function of the circuit depth. So in this case, the coherent noise has, if you want, visually rendered itself as an oscillation, and that's going to be a very common effect we see, where the error will initially be very large and will grow, and as time goes on, it may well shrink again temporarily, because effectively the noise has added up to be an identity at precisely the right angle here. And this result is for a specific noise strength of 3 degrees, so just a 3-degree angle. The reason that it looks so dramatic is that this sequence is going to amplify the noise. Because we've repeated the same noise gate d times, we've amplified the noise, if you want, d times in the angle, which then turns into this oscillation. So in fact, this type of template sequence where you take a noisy gate and repeat it many, many times is a perfect way to amplify the noise, to study the noise, and to characterize it and understand it. And in fact, it's used in the calibration of the gates. So how does this compare to our real experiment? Here, for comparison, on the left, you have the full experiment, which we saw earlier. That's why I wrote real. And you notice a visual similarity between the full experiment data on the left, which is still overall noisier and so on, but overall it follows exactly this type of oscillation, although it's a decaying oscillation, so we'll see why that is later. It has to do with incoherent noise. But overall, we've been able to reproduce one of the main visual aspects that we saw in our data, which is precisely this pinching and revival of the noisy data. And it happens that in this case, in fact, our gate was purposefully miscalibrated to about a 3-degree angle over rotation. So that's exactly what we see here. Now, in the next step, let's see how the error scales. One thing you can notice also before we move on is that the decay isn't due to the coherent noise, it isn't due to the coherent oscillation. So that's an important feature to know, is not due to coherent noise. Also, notice that none of the fluctuations that we observe here are due to the coherent noise either. Those have to do with the other noise sources. Notice that we do not start nor end at +1 or -1, also not due to coherent noise in this case. Those features are due to the other noise sources. Okay, with that, moving on to the scaling of that noise. Let's analyze the performance of the algorithm, okay? And the message here will be that coherent errors have, in general, quadratic worst-case performance. Or if you want, coherent errors have a quadratic impact on the algorithmic accuracy. The worst-case error can grow quadratically to first order. And that's precisely because of this coherent buildup. The way we can estimate or write this out more analytically is to take the noisy expectation value of z, which I'll denote here by z tilde, and just subtract from it the ideal expectation value. In this case, this is going to suffice for our purposes. So let's plug these in and see what happens. On the left here, we'll have the cosine of d pi plus d epsilon. From it, we'll have to subtract the cosine of d pi. And at this stage, we can begin to use our usual trigonometric identities, remembering that cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a sine of b. So using that to substitute in the expression above, let's put that in brackets, we'll find that we have the cosine of d pi times the cosine of d epsilon minus the sine of pi sine of d epsilon minus again the cosine of d pi. Okay, and now we'll notice that sine of, oops, I think this one should be like that. Now we'll simplify this and find that we have -1, substituting again the fact that cosine of d pi is -1 to the power of d. So we have -1 to the power of d times the cosine of d epsilon -1. Okay, this here is essentially our ideal value, and this is our noise. And we're going to look at the difference between them to first order. So now we can use the fact that cosine of x, let's say, to lowest order in the Taylor series expansion around x equals 0 is 1 minus x squared over 2 plus some other things of at least order 3. So writing out the above expression again, which is our error, is we're going to find that this is minus 1/2 minus is going to be equal to minus 1/2 minus 1 to the power of d d squared epsilon squared plus order of epsilon cubed. So you notice that in this case, as a function of both the depth and the error, the error scales quadratically in the expectation value. It goes like epsilon squared in this case. A brief summary of coherent errors is that they're ubiquitous. As we saw, they can be described by unitary operations and lend themselves to a nice decomposition in terms of a unitary followed by a unitary. They don't lose quantum information since simply their constitution is another unitary, but they can rotate and skew it and mask it from us. In the data, they can create oscillations, just like the one you see here depicted on the right. And in data, they also don't yield exponential decays. They don't explain a lot of the other noise we see. Ultimately, they have a quadratic impact on the algorithmic accuracy, the worst case error. Now, coherent errors at the single qubit level are already very important, though typically they're relatively low, and in fact aren't usually the dominant noise mechanism. However, coherent errors at the multi-qubit level, or quantum crosstalk as we like to call it, can be much more significant. And if you'd like to know more about that, we'll dive into that in the bonus content, where we'll look at an example of a 2-qubit coherent ZZ error. While the physics of it may seem very different, and it has to do with entanglement, and it's a different Hamiltonian and so on, the algebra is almost the same. We won't really change anything. Effectively, we'll look at a Hamiltonian that has a ZZ coupling between 2 qubits that's always on, and we'll do an experiment where we can see what its effect is. But essentially, we'll have exponentials with arguments that will expand, we'll add rotations, we'll still do the same decomposition of a noisy gate preceded by a noisy unitary operation, and the conclusions will be more or less the same. So with that, I'd like to pose the following 2 questions to you as we come to the end of chapter 1 of our journey, where we've covered coherent errors. Answer these multiple choice questions in the chat. Type them up, light up the chat with your emojis and responses. The first question is, and I will give you the answers later. The first question is about coherent noise. Coherent noise can be caused by A, loss of energy of the qubit, B, miscalibration, such as over-rotation, C, wanted coupling to neighboring qubits. Question 2, coherent noise can be really bad because A, it results in loss of information, B, you cannot undo it, or C, the worst case error often grows quadratically. So type up those answers in the chat and see what everyone else is responding. Pause the video, think about it before we move on. Okay, I hope you had the time to answer these questions. If not, here are the answers. Coherent noise can be caused by a lot of things, but in particular here, it's not the loss of energy that will be incoherent noise. It's really miscalibration in this case, such as over-rotation, which is the example we covered. It can also be caused by unwanted coupling to neighboring qubits. Here, the tricky question was that I specified wanted coupling. On question 2, coherent noise can be really bad because it doesn't actually lead to loss of information. No information is lost. You've simply done a different algorithm than you wanted to do. So information isn't lost. It's recoverable. In fact, there are protocols such as dynamic with decoupling which allow you to recover that information in certain situations. B, you cannot undo it. We haven't talked about this yet, but you can undo it. Again, because it's a unitary, any unitary has an inverse. There's no loss of information. We can characterize the error and undo it. That's known as error mitigation often. We'll touch on that at the very end of this lecture. But that's not the answer either. The answer is C, because the worst case error can grow really badly. Not always, but quite often that can happen.